All right, in this video we're going to be talking about polyprotic acids. What that means, they're a category of acids. All that really means is that they have more than one H plus available to be ripped off or to donate. Okay, we're going to look at two examples, and each one has its own subtleties, I guess. Okay, so the first one we're going to look at is phosphoric acid. Okay, it's one of the ones we had to learn the name of last semester. It's a pretty common acid. Yeah, but it has 3 H pluses. I would love to tell you, oh yeah, they all pop off as you get 3 of them. The end. Great. What really happens is that they each come off one at a time, and each one has its own Ka value, which makes this a little complicated. So the first Ka is when this dissolves in water, you end up with H2PO4 minus, because one of these H pluses has been ripped off, you get an H3O plus. It's supposed to be an H3O, sorry. And there's a Ka value for that, kind of running out of space. And it's 7.1 times 10 to the negative third. Great, just like any other Ka we've seen, nothing special so far. Now, it turns out that this, although it is the conjugate base of this thing, has acidic protons. So under the right conditions, it can still keep popping off H pluses, protons, whatever. So this could act as a base and rip off yet another one. And we get another H3O plus produced. And this is the second reaction, so I'm calling it Ka2. Its value is 6.8 times 10 to the negative 8th. Okay, and we can keep going where this product can also lose an H plus. And we get PO4, 3 minus. We finally get phosphate. Okay, and there's a third Ka, and its value is 4.3 times 10 to the negative 13th. I don't need you to memorize these Ka values, but we're going to look for trends. We're going to kind of look for how this matters. Okay. The first trend is that each acid, so each proton as it comes off, the Ka values tend to go up by about a factor of, or they seem to get smaller by a factor of about 10 to the 10th. 10 to the 5th. So from 10 to the negative third to 10 to the negative 8th is a factor of about 10 to the negative 5th. So what this really means for us is that if you dissolve this in water, the first Ka is the only one that matters because it is 10 to the 5th times difference. So it is 10 to the 5th times as likely to produce an H plus. So in other words, for every one of these that is going to react, you're going to have, what's 10 to the 5th? 100,000 of these. So you can almost ignore the impact that this is going to do. And this is 100,000 times less likely to be produced than this one. So in other words, if you dissolve this in water, only Ka1 matters. Because Ka2 and Ka3 are so small that we can basically ignore them. Basically, what I mean by this is this first reaction is going to happen, and after it happens about 10,000 times, so for every 10,000 of these that happens, you're only going to get one of these, which means, in the grand scheme of things, it's not going to really drastically impact the answer. And for every 10,000 of these, you're only going to get about one of these, because every time we change this by about a factor of 10 to the 5th, which is about 10,000. Okay. And here's the other thing, is that Le Chatelier's principle starts kicking in and messing this up. Le Chatelier's principle almost stops the second reaction anyway. Second and third reaction. Because a bunch of H3O plus is produced, or is present. So at the end of the first reaction, we have some amount of H3O plus. And so every time this second reaction is trying to occur, all the H3O plus from this first reaction is here. Basically, we increase the products, it's gonna shift things to the left to make this reaction not really happen anyway. And since the second reaction probably isn't gonna happen, we're never even gonna get to the third one. Okay, but that doesn't mean that we can always ignore the second two reactions out of the three. It turns out that since this has 3 protons, if you start titrating this, so if you pour base into this, H3O plus a base, it'll rip all of them off because it's essentially a Le Chatelier's principle. The base is going to react with the H3O plus, and it's going to remove it as it forms, and it's going to pull the reactions to the right, and it's going to do it to all 3 reactions. So you essentially rip all three H pluses off. So all 3 H plus get removed. So, in the grand scheme of things, H3PO4 has 3 acidic H pluses, but if you dissolve it in water, we only care about the first one. You only get 1 H plus. If you titrate it, it will rip off all 3. So basically, if you put it in water, we only get 1. If you throw it in a base, you get all 3. And it's based on the difference in the Ka values and Le Chatelier's principle. Okay. Wait a sec. I guess this is page 13. Okay. Another example that I want to talk about is H2SO4. This one's a little different because it's a strong acid. It's one of our list of, we had our 7 strong acids. This is one of them. So there are 2 protons, and the first one is essentially, because it's a strong acid, goes to completion, no Ka value, no reverse reaction. The second reaction, this HSO4, is a weak acid, so it has a Ka value, but it's actually a pretty strong acid, even for being a weak acid. Oh, I did it backwards, but sorry. And this Ka2, because it's the second reaction, is 1.1 times 10 to the negative second. So if we actually compare this to the previous reaction, it turns out that the second reaction is a stronger acid than any of these 3. Because 1.1 times 10 to the negative second, 10 to the negative second is bigger than 10 to the negative third, 10 to the negative 8th, or 10 to the negative 13th. So these are both pretty strong acids. The first one is absolutely a strong acid. The second one is pretty strong. Okay. This actually makes things complicated for us. It turns out that if you have a very high concentration, it turns out anything above like 0.5 molar, you're going to produce so much H3O plus that Le Chatelier's principle is going to stop the second reaction. So, if concentration of H2SO4 is greater than 0.5, only the first reaction matters. Okay. If you have a very low concentration, so if concentration of H2SO4 is less than 0.010 molar, both reactions go to completion. Because this is a very high Ka value, essentially, if you have a very low concentration, this H3O plus won't be high enough to stop the second reaction. They'll basically both go to completion, and you don't have to do the equilibrium stuff. The complicated bit is if you're in between those values, So if the concentration of H3O or H2SO4 is in between 0.001 and 0.5, the first reaction always goes to completion. The second reaction, you're going to have to do the ice method. Because there's a Ka, you'll actually have to go through all the legwork of the equilibrium stuff. Okay. So let's try one of each of these scenarios. The third one's going to be miserable. Sorry. Okay. So let's try an example. We want to know what is the pH of a 0.750 molar H2SO4 solution. Okay. Well, based off of these things, since it's above 0.5, we only have the first reaction. And since it's a strong acid, we literally just take the negative log of the pH, basically, or the negative log of the concentration. So the first reaction happens and the second one doesn't happen at all. So for every 1 mole of this, we get 1 mole of H3O plus. So our concentration of H3O plus is 0.750. So pH equals the negative log of 0.750. And that value comes out to 0.125 molar. So, or not molar, sorry, no units on pH, but 0.125, which is really, really acidic. Okay, makes sense. It's a strong acid. We have a pretty high concentration. Nothing too weird there. If we had a really low concentration, so something below 0.001, so let's make it a whole factor of 10 lower. So, so the pH of a 0.00010 molar H2SO4 solution. Well, essentially what happens is we say that both reactions go to completion. So for every 1 mole of this, we get 1 mole of H3O from this, and then the second one's also going to go to completion, so we get another mole from this. So we essentially just take this times 2. So the concentration of H3O plus is equal to 2 times this because we're getting both H2s off of here. That's supposed to be H2SO4. Sorry. So pH equals negative log of 0.00020 molar, and we get 3.7. Okay, so if you have a high concentration, you get 1 equivalent, so 1-to-1 ratio. If you have a very, very low concentration, both reactions go forward, so you get 2 H3O pluses for every 1 mole of this, so it's 2 equivalents. Okay? Things get real messy if you're in between that range. So let's say we want to know what is the pH of a 0.100 molar H2SO4 solution. Okay, well, the first reaction, we're going to treat it as a strong acid, goes to completion no matter what. Right? So we have our 2 reactions. The first one always goes all the way forward no matter what. Okay? So what that means for us is the concentration of H3O plus is going to be equal to 0.100 molar just from the first reaction. Okay? The second reaction, we're going to have to go through all the ice method stuff. Second reaction, this is not division, I'm just dividing these things. Sorry, make it a squiggly line, I guess. We'll check the assumption. Okay, I've been trying to do the assumptions in blue. Let's keep doing that. So the assumption is you take the concentration divided by Ka, which is 1.1 times 10 to the negative second, and this comes out to 9. So this is less than 100, so we have to do the quadratic. brownie face, I guess. All right. So what that means for us is we're going to have to do the ice method and the entire quadratic equation thing for this second reaction. Second reaction looks like this. H2SO4 minus, or sorry, HSO4 minus, because it's the second reaction, forms an equilibrium in water to form H3O plus and SO4 2 minus. And Ka is 1.1 times 10 to the negative second. So the rest of this is an ice method problem. It's about to get a little messy here. So the initial value is 0.100. We don't have any of that, or we can ignore that, and these are both zeros. This is going to decrease by some amount, and these are both going to increase by that same amount. So 0.100 minus x, and this is x, and this is x. So Kc is products over reactants raised to the coefficient at equilibrium. So Ka is 1.1 times 10 to the negative second is equal to x times x, which is x squared, divided by 0.100 minus x. Unfortunately, we can't get rid of that x because the assumption didn't work, so we have to do all the legwork. And x will be equal to the concentration of H3O plus. So we're going to multiply both sides by 0.100 minus x to get this out of the bottom. Okay, which gets a little messy. That's okay. So this cancels out with that. Over here, 0.1 times this would be 1.1 times 10 to the negative third. Basically, we took this, or divided it, or took it times 0.1, minus 1.1 times 10 to the negative second, x, is equal to x squared. Okay, to get this to the other side, we're going to subtract 1.1 times 10 to the negative third, and we're going to add 1.1 times 10 to the negative second. Okay, on this side, they're both going to cancel out. Over here, we got to do both of these things. I'm going to add the 1.1 times 10 to the negative second first, because I want that x, and then minus 1.1 times 10 to the negative third. So this side is basically equal to 0, so we're in the ax squared plus bx plus c format of this. I'm going to rewrite it just so it's clear. That's a 3. It's equal to 0. So a is equal to 1, b is equal to 1.1 times 10 to the negative second, and c is equal to negative 1.1 times 10 to the negative third. So plug everything into the quadratic. So it's negative b, so 1.1 times 10 to the negative second. Plus or minus, we only care about the plus value because we don't need negative numbers here, times b squared, which is 1.1 times 10 to the negative second squared, minus 4, a is a 1, times c is negative 1.1 times 10 to the negative third. All of that over 2a, and a is a 1. If you type all this in your calculator, plug everything in, I'm not going to show it real fast because I've got the answer already. X comes out to be 0.028 molar. And X, the reason we're solving for it is the concentration of H3O plus. Yay, we did all of that. Well, the concentration of H3O plus, we would normally take the negative log of this, but this is the amount of H3O plus from the second reaction. We also have all of this H3O plus from the first reaction. So we need to add those two numbers together. So the total amount of H3O plus is equal to 0.1 plus 0.028. So the 0.1 is from the first reaction and the 0.028 is from the second reaction. So we get 0.128 molar. So pH is the negative log of that. Or sorry, negative log of 0.128 molar. And we get 0.893 as our pH. You'll note these things suck. Sorry. It's a little messy having multiple reactions where the first one's a strong one and the second one's a weak one. If you're in that middle range, there are no values where the assumption works, so you have to do the quadratic literally every time. For the first reaction goes to completion. The second reaction, you have to do the quadratic every time. These things are messy at best. Sorry. Thank you.